So our first speaker will be Lyndon Emsley from EPFL. You all know Lyndon. And he will talk us about the atomic level structure of porous materials by NMR crystallography.
So yeah, I want to talk about characterization, I guess, of porous materials and how that can actually contribute to the development in the future of better functional systems and a better life through chemistry, of course. Now, in this particular audience, though, I got a hard job because I'm an NMR spectroscopist, and so I think the subtitle of my talk, right, is NMR, Why Bother? So many of you thought about NMR several years ago. Maybe some of you did some NMR. You thought it was okay, but then along came something like electron microscopy, for example, and you just thought, oh, well, those pictures look much easier to interpret than all that NMR stuff, so I'm not going to bother. I'd like to report back to you a few years later with a few examples, a kind of update. I'm not going to go into a lot of detail for this audience in the technical details. I'm not going to go into details of each of these projects. I'm just going to give you an overview of what NMR is doing today and try and convince you that it has changed radically and that you probably should go back and start doing NMR again if you're not already. And my talk is going to be based around a concept of crystallography, what we call NMR crystallography, in analogy to X-ray crystallography. And the idea, of course, that we're going to apply it to things that aren't really crystals. So that's, crystallography's kind of become in chemistry to mean structure determination. So we tend to talk about crystallography when we determine structures. The really interesting thing to do today is to determine structures of things that are not crystalline, or which are composite or multi-scale. And I'll try and show you that solid-state NMR is probably the best technique to look at atomic level structures of multi-scale or multi-scale objects. So if we are thinking of crystals, then this is the way I see utopia. Utopia is an imagined community or society that possesses highly desirable or nearly perfect qualities for its citizens. A lot of people think that's France, but I moved away from France now, and I can see from the outside it's not quite true yet. So in utopia, of course, crystallography will play a central role, at least in my vision of utopia. And this means that people will have to be able to take powders, maybe a chemical structure of what they think is in the powder, they're going to put it into a black box, and they're going to get a crystal structure out of it. And so what's in the box? So in utopia, what's going to be in that box is almost certainly DNP-enhanced NMR, in combination with some form of high-performance computing of NMR parameters. So, for example, chemical shift-different structure determination would be the method that we're pursuing at the moment. And then I want to tell you something that you probably don't know. There's a lot of excitement this year about electron diffraction determining structures of tiny little crystals. Okay? Well, all due respect, it's beautiful stuff. 3 angstrom resolution. I mean, 3 angstroms, guy, we're chemists. I mean, that's like gigantic. But anyway, I can take a powder with NMR today and determine a full crystal structure. This is an example from a drug molecule, ACD8329. It's a powder sample, and we determine a full crystal structure with an RMSD, which is actually slightly better than the single crystal X-ray diffraction structure. Okay? And when I say today, I mean 2013, so since 2010. So for nearly a decade, we've actually been able to determine structures from powders by NMR. And it's a little bit weird that you probably don't know that. So that's going to be my starting point. I'm going to try and talk about systems to illustrate where solid-state NMR is. I'm going to try and talk about systems that might be of interest to you. And so last night we were talking, and I get the impression that we're not quite sure what porous means, and I guess that's one of the points of Clément's introduction as well. So this may qualify. It's a coordination polymer that takes up CO2. One of our colleagues in Lyon developed this and couldn't solve the structure by any other method, and that's usually when they come to us. So these are very difficult problems. And again, we can do chemical shift-driven structure determination on these molecules. We determine chemical shifts, we compute them, we look at the structures that it's compatible with, and we come to a full 3-dimensional model, in this case, of what is a slightly disordered structure in these complex CO2 organic framework materials. So that's one example of where we can get to structures. in my group, we're having a tremendous amount of fun at the moment with perovskites. It's a very, very hot topic. Of course, you probably, unless you're living in a cave, you've heard of perovskites and their renaissance in terms of functional materials. And these materials have been characterized extensively by electron microscopy or X-ray diffraction. And for these materials, those are both very poorly adapted methods, really. And just on the left, I'm not going to go into this, I'll tell you why in a second, but on the left you can see what the previous conviction was about the structure, phase composition, cation doping in perovskites from other methods. And from NMR we can clearly see that basically it's random. So half the time they got it right, and the other half the time they got it completely wrong. Okay, so, and the NMR answers here are ambiguous, and you can see from, if you're interested in this, go and see this stream of papers which is being produced at the moment. Now, I'm not going to talk about perovskites because I don't think they are porous, right? Even by the most generous definition. Of course, you can put intercalation things in them, but I'm not sure that counts. And when I was preparing the talk, Clément actually wrote to me and said, please keep your thinking porous. And I told him that my thinking is almost always porous, but that I would be happy to talk about porous solids in this case. And so that's what I'll try and do. So maybe an example of our approach to structure determination illustrated on a metal-organic framework, and I'm pretty sure that qualifies today as a central form of porous material. So metal-organic frameworks, here's an example of a material called SIM1 made by my colleague in Lyon, David Ferrosing. And in this case, the problem is such that we know what the framework is. We know this is a ZIF framework, and diffraction will tell you that too. But they have substituents on the linkers, and you can see that this substituent can take up two different orientations, and they couldn't solve the structure by X-ray diffraction, even though this material looks highly crystalline. The crystallinity comes from the order in the framework. When we do simple one-dimensional magic angle spinning NMR, this is our proton spectrum down here, and you immediately see why there might be a problem. You immediately see that each of these groups, each of these protons has two chemical shifts. And so that's telling us that the linker must be in two well-defined but different orientations inside the crystal structure. So the question becomes, what is this crystal structure that is compatible with two different environments of the linker? Okay, and this is completely unambiguous. These are very well resolved for this kind of spectroscopy lines. And so it's also telling us that it's a highly ordered structure. It is not a disordered structure. Okay, so we don't just have a random set of linker orientations. And so we can then say, well, the first question is to know what are these resonants, who's who in the spectrum, and so we'll use two-dimensional NMR just so that we can say, well, okay, it's this proton, and that proton are in one conformation of the linker, and this one, and that one are in the other conformation of the linker. We can also do two-dimensional experiments which will not only give us that linker connectivity, but will also tell us what the proximity between the different groups in different linkers is, so interlinker connectivities. So we can take that on board. How do we do structure determination? Well, basically, we're going to make, in this case, it's fairly simple. So for us, we can actually take all of the different possible candidate structures, calculate chemical shifts using DFT methods, and these are very accurate today. There's been a revolution in how we do this, and compare it with our experiment. Okay, and for example, you can see that this structure and this structure both produce only one environment for the linker, so they cannot be right. This structure, well, there's a very small difference here between the two linker environments, but it's nothing like what we see in experiment. Yes, again, none of these structures so far agree with the data. So here we have the fifth candidate, again, nothing like agreement. Here we have something that's not, well, you know, it's the right order at least. Okay, so we see a small splitting here, small splitting here, larger splitting here, so they're all in the right order. It could be that one. But in fact, this strict structure does not agree with the interlinker distances that we measured, and so that cannot be the structure either. Okay, so actually none of these single unit cell arrangements agrees with the data, and this explains why you couldn't solve the structure by X-ray. It's not actually a simple unit cell. And so we have to think, okay, well, what could it be? It could be disorder. I've always said if we just had random orientations, that would lead to broad lines in my spectrum. And again, it's very clear that's not the case. So it's not a random distribution of a disordered structure. And so we have to go to supercells. And so we look at a supercell here, for example, a supercell structure which is made up of permutations of 1 and 2. And if we look at the structure of 1 and 2, then we get these two spectra, which would be superimposed. And this agrees very well with the shifts that we observe. So this agrees to within what we would usually consider indistinguishable error. And we also have a 2 by 2 by 2 supercell structure that will provide us with the right interlinker connectivities in the material. And so in fact, what we can do here is determine de novo this supercell structure for the material. And then when we predict the PXRD pattern here, for example, which didn't lead to solving the structure, we get good agreement. It's not perfect agreement because obviously this structure can have defects. Those defects, as long as they occur only maybe once every 20 unit cells, won't make any difference to the NMR. Okay, but they will mean that the PXRD says, no, it's not quite that. And so the PXRD, which is a kind of black and white technique, will say, no, it's not quite that symmetry. So it's interesting to see here that NMR can solve the structure where PXRD will never be very happy. And just to point out other developments, all of the things I'm going to tell you about today, or a lot of them, are based on being able to calculate NMR chemical shifts. That's electron density of the nucleus. It's a difficult problem. And as I said, tremendous progress being made. But for example, for those MOF structures, those DFT calculations took weeks, I think if I remember right, at least days. And today, to calculate, for example, in cocaine, will take you hours, typically. And so it's a bottleneck, and we've actually overcome recently this bottleneck. Of course, again, if you haven't been living in a cave, you've heard about the revolution that's coming along in chemistry, chemical sciences, with machine learning methods, and especially in computational methods. So together with Michele Ceriotti at EPFL, we actually developed machine learning methods to produce chemical shifts to DFT accuracy, except, of course, we can do that now in minutes or seconds rather than hours. And so this is changing the way we can approach structural problems as well. And if you want to go and have a go or see more about that, then go and have a look at our website. Okay, the main question I wanted to ask today, for example, is if you're in a porous material, so it's an SBA type material that's been built for catalysis or some functional properties, then inside the pores you have a silica surface which is slightly disordered, and on that surface you have some kind of active site. And for example, if you have a ligand, so here's an example with my colleague Christophe Copperet, who's trying to do single site catalysis inside porous materials. Okay, and this is his ligand with, in this case, a platinum complex. That could be a more interesting metal here if we wanted to. And the question is, can we use NMR to go from this chemical structure into a full 3D structure of the molecules on the surface of the material? Okay, and you would have thought, well, that sounds like an easy thing to do. Or maybe you don't, but it sounds like it's something you could do, right? So I'm going to ask you a question. What do you think the structure is? So it's like pick a card, any card. So I'll give you some, and you can make up whatever you like. Here's some choices. You could imagine that ligand, for example, is completely disordered. There's no particular preference, it's going to be completely disordered, and there's just been a cloud of structures. So we're going to start asking ourselves, what does structure mean in these disordered systems? Okay. But then you might say, okay, well, I'm a bit more chemical knowledge, so it's probably not likely to be completely disordered. There might be some affinity of this group for the surface, in which case I might have a distribution, for example, of structures on the surface. Okay? Or alternatively, there may be repulsion, and so there may be a distribution of structures which are kind of pointing into solution, this kind of thing, right? And maybe it's a single well-defined structure. So think about what it might be. And now, the interesting thing is, you're thinking of this right now, and you're probably, there's a distribution of answers in the room. And why is that? Well, if you think about it, it's because you don't know what the structure is. And, you know, often in chemistry, you do have a good idea. Why don't you know? Well, actually, it's never been determined. There are no structures of these kinds of things on disordered surfaces. Okay, so nobody's actually determined the structure. And I thought, oh, that's a bit odd, isn't it? So, you know, you think, what about these methods? And then you think, well, actually, all of these methods for surfaces are only going to yield partial structures, or in ultra-high vacuum on perfect surfaces or something like that. Okay? So I thought, well, that's, again, a bit odd, isn't it? So as a good scientist, in our day and age, I decided to go to the literature and find out if structures on surfaces were known. So I went to Wikipedia. And so if you look on Wikipedia, you find that effectively surfaces have an entry, so that means this subject exists, and that they have been analyzed. And you know, so what we find is indeed that most techniques for surface analysis require high vacuum, or they need to have, you need to look at very ordered structures on model surfaces. So we've always seen, you know, beautiful TEM structures of well-defined surfaces with benzene or today slightly more complicated molecules lying on those surfaces. Of course, that doesn't really count in terms of functional materials. Why not NMR? Okay, I'm not claiming that that NMR is suddenly a solution and that stupid people just haven't been thinking about it. No, why not NMR? Well, this is the problem for surface functional groups. So here I'm looking at an easy case. It's SBA15, so relatively high surface area. I just have some phenol groups on the surface with a relatively low concentration. And the result is that this is the spectrum I get. And I guess many of you have recorded this same NMR spectrum in the past, and which is why you're not doing it anymore. Okay? And so, obviously, we don't have enough signal-to-noise NMR. It's a very insensitive technique. All those other techniques, you know, high-energy techniques, are really sensitive. They can see those tiny amounts or tiny objects. But NMR can't. Okay? And so our question in my group became, let's see if we can do something about that. How do you do NMR beyond the sensitivity that's given to me by nature? And nature is the Boltzmann distribution of populations between the energy levels, which in NMR and the radio frequency regime is a very, very low energy. And so they essentially have the same population at room temperature. In fact, the polarization is 0.01%. Okay, so that means 1 in 10,000 excess in population between the ground state and the excited state. That's a very unusual situation. If you think of UV spectroscopy, you have everything in the ground state and nothing in the excited state when you start. Okay, so that's why and so what we need to do is find a way in NMR where we can go to a polarized starting state, and this would give me much, much higher sensitivity. So the question is, where can I find polarization? And again, I'm not expecting you to follow the physics of all this, just the idea. The idea is electron spins are about 600 times more polarized than protons than nuclei of protons. And so the question is raised, can we transfer polarization from an electron spin to a nuclear spin? That'll be our target. And there's some problems associated with that. First of all, yes, the answer is yes, we can do that kind of thing. So this is the 4-level system of an electron and a nuclear spin. You see the electron spins are polarized. There's a difference in population. Here, for example, I've schematized this with no difference in population across the nuclear levels. And what I can do is I can think, well, if I could tickle somehow this central transition, which is roughly at the EPR frequency, the electron transition frequency, if I could saturate that transition, that means make those populations equal, and look what happens. When I've equalized these two populations, I've created a polarization difference across the nuclear transition. So I've transferred polarization from the electron spin to the nuclear spin by radiating this transition or saturating it. That's actually the Overhauser effect. You've probably all heard of the Overhauser effect. You might have used it. The Overhauser effect between two nuclei in solution, two protons in solution, tells us about differences. Okay, but the original Overhauser effect was actually transferring electron polarization to nuclei in metals, so lithium metal, for example. And that's not what we want to do exactly, so the experiment exists. It means adding in situ high-power, high-frequency microwave radiation if we want to do this in modern NMR. So previously, the Overhauser effect was done at very low magnetic fields where we could use low-frequency microwaves. At 9 Tesla, this becomes 200 gigahertz. And so producing high power is a problem. That technology recently became available for a variety of reasons. And what we do today is we use gyrotrons to provide high-frequency, high-power microwaves that we can couple into an NMR magnet. And this typically can have several watts or several tens of watts of microwave power coming out here. So it doesn't have to be that efficient in terms of the coupling. Just to give you an idea, so this is high-tech experimental physical chemistry. This is my colleague Moreno Lely. He's showing you the gyrotron microwave source here, which also has a superconducting 9 Tesla magnet in it. And here we have the waveguide coming out, going across the room, and coupling into a magic angle spinning probe. I don't want to shine it in his eyes. Into a magic angle spinning probe here that operates at 100 Kelvin, because this is a low temperature effect, but we're in a solid, so it doesn't really matter. And this is the cryogenic system that's driving that. You can see that Moreno is Italian because he's speaking, although he knows there's no sound. So this leads us to the idea of surface-enhanced NMR spectroscopy, and that's one of the key things that we've been developing. How do we do that? Our idea is the following. We'll take a surface or a pore. Here we see a pore with the functional groups. This is where we want to see the NMR signal. It doesn't have, this is the signal, it's very small, okay? It doesn't have any unpaired electrons, so we can't do this Overhauser experiment. So the first thing we're going to have to do is actually introduce the source of polarization, the electrons, okay? And typically these are going to take the form of stable organic radicals, and we put a lot of effort into developing these polarization sources. You'll see that in a minute. We add that to the system. If you know anything about NMR, adding a paramagnet to an NMR system is bad. So actually remove some signal. Okay, so we're not doing very well so far. The idea now is if we irradiate this with our gyrotron microwave source, we'll induce polarization transfer from the electron to nearby protons. So we need some nearby protons, so we're implying there's some kind of propagating medium. We will get spontaneous effect called spin diffusion then, which takes the polarization around the electron, distributes it throughout the sample over the maybe micron range. So we'll have high polarization now here, and then we can use conventional NMR techniques such as cross-polarization to transfer the hyperpolarized proton magnetization to our surface of interest, and if we're lucky, this will magnify the sample. The way we found to do that, and this is what I was saying, is very simple. So we're going to take a porous material or a surface or pretty much anything, wet it, so incipient wetness, and we're going to wet it with a suitable solvent. So this could be tetrachloroethane, it could be water glycerol. And we're going to add our source of polarization, which is typically a nitroxide biradical today. These are very efficient molecules, and as I said, there's been a lot of development in this area over the last few years. We then freeze it. So this is easy to do. We just wet it at room temperature. We then freeze it down to 100 Kelvin and do our experiment. And at that point, this is the source of polarization at 100 Kelvin, and the frozen solvent is this transmission medium that allows us to transfer polarization from the radical to the surface. The result is spectacular. Okay, so the result is game-changing. Here we see that initial spectrum that I had before, and now this is the same spectrum taken in the same conditions, and all we've done is turn on the microwave radiation. And suddenly the spectrum jumps out as we get full characterization of this material, including some of the surfactant that was left over from the synthesis. So as I said, this is game-changing for NMR. Today we can get enhancements in the signal of about, say, 400, and the sensitivity goes as the square of that, so tens of thousands in terms of the experimental times required. Recently, for example, we've applied this to core crown structures in semiconductor nanocrystals. We've done the full 3D structure of CSH in industrially relevant calcium to silicon ratios. We've done a lot of work on the structures of silicated alumina catalysts, so either the bulk, the interface, or the surface in those systems. And very recently, we've actually been able to determine NMR signals from two-dimensional flat surfaces. So this is nucleic acids on glass supports that you'd use, for example, in microarrays. This is just completely impossible to do before. Let me give you an example in the things that are of interest to you very quickly. This, again, is a metal organic framework, and this was done with Carolyn and David. And the idea here is that they were interested in determining the nature of functionalized MOFs, here the peptide functionalized MOFs, and, for example, a proline functionalized MOF as compared to a glypro functionalized MOF. And, of course, you could ask them why they're interested in this. What we can tell you from NMR is now we can obtain natural abundance. We can't see, this is probably the only negative consequence of the screen resolution, but we can get natural abundance nitrogen-15 spectra from these materials. And again, that's just completely unheard of before. Okay. And for example, this is the proline nitrogen resonances, for example, in the amino acid in both cases. We see shifts between the different materials. And DFT and MD calculations that Carolyn can run allow us to unambiguously assign those shifts in a way that we can clearly identify strong H-bond interactions in the proline modified material with the surface OH groups. So there's an interaction between this and the surface. Whereas in this group, of course, that glycine is acting as a spacer, pushes it out into the cavity, and there are no longer these strong interacting H-bond groups. So we're changing the functionality of the material with this, and we're confirming the structures through actually relatively simple NMR experiments. Another example, the same kind of thing, is, for example, in tin beta zeolites. You probably know there's a lot of debate about the nature of the active site in tin beta. And here, for example, we can obtain natural abundance tin magic angle spinning NMR spectra. Again, completely unheard of. This would literally take months and months to acquire otherwise. These are obtained in minutes, 64 scans. We can see 3 different tin sites, that's known. And of course, what we can now do is look as a function of composition. We can see which of these tin sites changes. We can relate that to function. So we know which of the tin sites is now functional. Okay, so that's the first thing. And once we know that, we can again create structural models for the active site. Okay, we know something about the chemistry, and there's a question about open and closed active sites in tin beta. 5 minutes. And in that case, open and closed active sites, we create models, we calculate DFT by DFT, the chemical shift or the anisotropic parameters, and we can then actually assign a full structure to the active sites in tin beta. Okay, and then very quickly, the last couple of things I want to tell you about. The first is to come back to that original problem. Do we now have enough sensitivity to look at distances, to the distance measurement approach to structure determination for fragments on surfaces? And so we'd like to, for example, measure this distance. We can measure this distance to the carbon here, to the silicon on the surface between the nitrogen. These are all NMR active nuclei. We can measure the nitrogen to silicon distance here, and even the nitrogen in the TMS. So we have different silicons, different carbons, different nitrogens, and there are NMR experiments that allow us to measure distances if we have enough sensitivity, and then we can do that again here. So we can determine a network of different distances, and that determines a structure. Okay, so that's the other way to do structure determination, not chemical shifts this time. So for example, here's DNP-enhanced reador data. The dephasing, the decay of this curve tells us about the distance. And for example, I can fit that to the known, to the kind of distance I expect. I get 3.56 angstroms. So a very accurate measure of distances. What we're going to do is actually measure those curves for all of the system. Okay, so this network of distances. So I end up with 8 different dephasing curves. I'm then going to feed that into a modeling system. So this is how we determine structure in any case, whether it's by X-ray or by NMR. We calculate the reador curves. We compare them to experiment. We're also going to, of course, do XAFs in this case because you're the Platinum Center. We're going to feed that into our system, calculate RMSs, and that will produce a structure. And so here's the structure we find for the supported PT-NHS complex. Okay, so that's the full structure of the fragment on the surface. Okay, it agrees perfectly with the data to within error. Structure is stable when optimized by DFT. I don't know why anybody cares about that because it's just what happens in a computer. This is real life, but people like that. More importantly, perhaps we can do cross-validation error analysis and determine the positional uncertainty. So this is the ensemble of structures that fit with the data. And so I think we can go back to that original question, right? So the RMSD is about 0.6, 0.7 angstroms on the central structure. And so we can go back to that question. Which structure did you expect? And again, whatever it was, you probably didn't think of a single well-defined structure. That is, in fact, what we find. And there's a structure-directing interaction. So this platinum center is interacting very preferentially with the oxygen of the TMS groups on the passivating surface. Okay, so we find a single, well-defined structure. Okay, I can't stop without saying a little bit about something that we're doing with Clément, a very exciting project. Again, I'll just give you some iconic pictures. He's interested in producing core shell particles, and we're interested in imaging the structure of these core shell particles on the nanometer scale. So a completely different type of structural problem now. And we've been thinking about ways to do that. So for example, you might have a polystyrene core and then a silica crown filled here with CTAB. Okay, and actually if you think about it, what we can do is the following. This is our particle. We wet it with our polarizing agent. We irradiate with microwaves. What happens? Well, first of all, the polarizing agent gets highly polarized. That's what we've been doing so far. Okay, and the surface becomes highly polarized. Okay, but then if we wait, if this contains protons, the polarization will actually propagate into the particle. And the signal will build up as a function of time. The smaller the particle, the faster it will build up. The bigger the particle, the slower it will build up. So the buildup of this magnetization actually tells me something about the size of the particle. Okay, and so now if I go to a core crown system, for example, core shell system, sorry, what will happen? Well, the same thing. I polarize the solvent polarizes the surface, and then the polarization propagates into the material. This time, the signal from the shell, okay, that's the red signal, will build up quickly. And the signal, which is different, this is chemically different, so we have a different signal in NMR, that will only build up slowly. It takes time for the polarization to get to the core. And so I can compare these two curves. This is obviously on the surface, it's building up quickly, and this is obviously inside the material. It's building up only very slowly. And you can see that obviously if I understand the dynamics here and the details, what I can actually do is actually very impressive. I can actually fit experimental build-up curves here for the CTAB and the polystyrene to a quantitative image of the material. So I can determine that I have my radical solution, I have the CTAB layer, so the silica layer, and then I have the polystyrene core, and I know what the size of those is based on the quantitative fit here. And so we get something that's in very good agreement with a core size of 84 nanometers and a layer thickness of 90 nanometers. So I've run out of time. Thanks to my many, many collaborators. I mentioned many of them as we went through the talk, so I won't talk about them again. Talk about my group. So here's the people that actually did this work, of course. So the people directly involved in the kinds of things we've been talking about today are Brennan, he's now in the US, Federico, who's just finishing, Albert, who's just finishing. Arthur Pinon did the work on polarization waves, and a whole large group of people. So thank you very much for your attention.
Thank you, Lyndon, for a fantastic overview. So we